How about now? Audible?
Yeah. Oh, yeah. Yep.
So it's audible and reverb? So still audible? Good. All right. Insanity is doing the same thing and expecting a different result. Here we do the same thing and we do get a different result, and they're always the unintended ones. I sent you a Zoom update. All the faculty, all the students should have seen this. So there's just a little more added security. I guess what's been happening is people from anywhere can come onto these lectures. I don't know why the university's worried about that, but I guess hackers can get in that way. So this is review. We looked at fluid statics, and what we developed was that when we just have acceleration due to gravity operating, there is no change in pressure in horizontal directions. Okay. No change in pressure in the horizontal directions. And we will see a change in pressure in the vertical direction. Again, we started out with partial derivative. Once we found out that the other horizontal coordinates weren't involved, then we got from that ordinary derivative. And again, instead of looking at z direction being positive upwards, we could look at the h direction, which is positive downwards. And the reason for that is in either case, the positive or increasing pressure direction is downwards. So we also define what a free surface is. It's where you have a liquid atmospheric surface. And at the free surface, we know that we have atmospheric pressure. And if you're working in a gauge datum, we set local atmospheric pressure to 0. 0 psi, 0 Pascal, 0 Newton per meter squared, 0 atmospheres. When your atmospheric pressure is non-zero, you're typically using the absolute pressure measurement data. And you can certainly do problems in one or the other, but you can't mix and match. To get from an absolute pressure to a gauge pressure, we have to subtract off atmospheric pressure. So again, from the free surface, we just take advantage of the fact that now we can integrate from the free surface and we get a very simple result, and that is that when we integrate that, this is the equation we had last time from a free surface. In general, this only works from a free surface. You can't just use it anywhere. You have to have that free surface because this is a result of an integration and using the boundary conditions where we have 0 for h at the free surface, so the datum is up there, and the atmospheric pressure is gauge pressure, and it's 0 at the free pressure surface. So we also integrated the general forms of the equation, and when I say the general forms of the equation, what I'm talking about are these. We also integrated the general forms of the equations, and what we got were, for example, P1 over gamma plus Z1 is equal to P2 over gamma plus Z2, or P1 plus gamma Z1 is equal to P2 plus gamma Z2. And then we use that when we were looking at, for example, manometers, or where we had multiple fluids in systems. So what this allowed us to do is calculate pressures anywhere in these fluids, or where we had piecewise continuums, that is multiple fluids, we can still calculate pressures throughout the systems. So what I want to move on to today is forces. So what we want to do is calculate the pressure distribution over any surface, plane, submerged surface. And from that, calculate the force that represents that pressure distribution, as well as where that force acts. Once we get the force, then you can do structural design or any other kind of design you want. So if we're looking at one side of the surface, so again, we're going to be looking at submerged surfaces, submerged plane surfaces first. And so, for example, for a dam, we have water on one side of the dam, no water on the other side. So typically we look at just one side. Could you have fluids on both sides? Of course. And that would just be an additional calculation where you're now calculating the force on both sides of the structure. So not uncommonly, if you have a tide gate somewhere, you've got a water depth on one side of the tide gate and a water depth on the other side of the tide gate. And you'd be calculating the forces from both sides on that tide gate. So we're going to start off walking, and we're going to look at a very special case of a plane submerged surface. And that is a horizontal surface. So again, it can be irregularly shaped. It could be a nice rectangle. But when we have a horizontal surface, what we know is that everywhere on that surface, the depth of submergence is h. Some books use y as the vertical axis, which is unfortunate because your book and most of this course, we use x and y for horizontal dimensions. So in this case, h is positive downwards. Since you have a horizontal surface, everywhere on that surface, the submerged depth is h, and therefore everywhere on that surface, the pressure distribution is gamma h. So again, if we look at the pressure distribution, the pressure everywhere on that surface is gamma h. And remember, pressure is a scalar. At a point, it's acting the same in all directions. So let me move this. So if we look at, again, the definition sketch in the lower right-hand side from the previous slide, what we would have is the pressure everywhere on the entire surface is gamma h. If we look at an individual strip, so if we picked an individual strip running along this surface, the pressure on that little strip is also gamma h. And what we're after is we want to represent this pressure distribution as a force. And, for those of you who suffered through statics, this is basically a uniform load, just like the snow load on the top of a building. So what we get from this should not be surprising to you, but again, we're walking before we run. So whether we're looking at the entire surface or whether we're looking at just a differential strip, in this case dA, the differential force dF on dA is the pressure acting on dA times the area dA. And again, the pressure on dA as well as everywhere on the surface is gamma h. So what we're after is integrating all of the little dF forces acting on each little dA. And when we integrate all of the little dF forces over the area, what we should get is the total resultant force. And what we can do is now put this substitution into dF. So the integral over the area of PdA is going to give us the integral over the area of dF. And when we make that substitution, obviously the integral over the area of PdA, which is gamma HdA, the pressure everywhere is constant. So we just pull that out of the integrand. And the integral over the area of dA is just the area, A. So basically, this resultant force is equal to the pressure acting everywhere over the surface because it's a constant pressure because it's a horizontal surface times the area. Kind of something you would have guessed at if you started at this. And remember, let me see if I can go back here. If you look at this, the pressure on any one side is P, which is gamma H. And when we calculate F equal to pressure times area, that's equal to gamma H, that's the pressure times the area. HA is basically the volume above the surface, right? H times the surface area is the volume above the surface. And when we multiply that by the specific weight, that's the weight of the material above you. Again, this should be completely obvious to you that the higher the snow depth on top of the roof, the more weight. What's that weight equal to? The snow depth times the roof area. The force is a vector, and it has the properties of a vector, magnitude and direction. Because the pressure distribution is everywhere normal to the surface, the resultant force is normal to the surface. The pressure is a scalar. It acts the same in all directions. Force is acting normal to the surface. It reflects the pressure distribution normal to the surface. Question?
Is that P equals gamma H or P equals partial derivative H?
That's a gamma.
Okay.
Always ask questions about my handwriting. The technical term for my handwriting is it sucks, but it's not getting better with age. So don't ever feel bashful about asking about what I write. So what I was just going through is the force in this case is the weight of water, which is basically the volume of the pressure prism. I say the volume of the pressure prism, that includes gamma. If I was just talking about the volume of the fluid, that would have been HA. But the volume of the pressure prism is including the gamma term, gamma HA. So again, what we found was for a horizontal, and this is what's key, because the pressure everywhere is constant, the resultant force is just that constant pressure times the area. And that pressure is gamma H. Okay. Again, you probably would have been able to figure this out yourself without any calculus. And as I mentioned just previously, the force is a real vector, magnitude and direction. So, if we're to structurally design something, we need to know where that force acts. As I showed you in the introductory slide when we were talking about a dam, one, you're using that force to make sure that the dam stays in place using sliding friction. But the other is you don't want the dam to rotate. And so you also have to do a moment equilibrium. And so typically when we are looking at stability problems, we're using Newton's law first law in two ways. One, sum of forces equals 0, but then we'll also be looking sum of moments equals 0 about some point. And so in that second one, that's where we need to know where the forces act. So in this case, again, it should be kind of obvious where the force acts, but we're going to go through that exercise anyway. So again, the force represents the pressure distribution, and we're looking down on top of this horizontal surface. So you can see the XY plane. We're just looking down on top of this instead of at the edge. And we have a total surface area of capital A. And we can look at individual strips. And the force is going to act, as you'll see, at a place we call the center of pressure. The area has a property of an area in which the area has a centroid. And that centroid is, for example, let's say it's right here. Oops. And that centroid has some either X bar or Y bar locations to the center of area. And then if the force is acting over here, that center of pressure is XP away from the y-axis and YP away from the x-axis. So again, the center of pressure does not necessarily act at the center of area. Now in this case it should, because you have a uniform pressure distribution. That's what we should find out. So what's typically done in order to assess this is to recognize if we take that force, the total resultant force F, and its moment arm about either the x or the y-axis, that would be equal to the integration of the force acting on little differential strips with the moment arm of each differential strip to the same axis. So that's basically what this text says. Resultant force F and its moment about any axis must be equal to the sum, the integration of all the moments of the distributed pressures acting on little differential strips dA. And we'll look at that graphically, but what this basically says is, this is the resultant force we just calculated. It's the pressure times the area, gamma HA. And we're trying to find out this. What is the location of where this force acts? And again, it's got coordinates xp and yp in the xy plane. We expand F to PA, and this is xp again, and this would be the moment arm of each little differential strip dA with each little force dF acting on it. And if this is the y-axis going into and out of the board, dF has some moment arm x. And so what we're doing is we're slicing this area into strips parallel to the y-axis. There's strips of area dA, and each one has a different moment arm x to the y-axis. So we take the equation from above, and little dF is equal to PdA, no PdA. So the left-hand side over here is staying the same. We expanded the right-hand side, and since the pressure all over the area is a constant, it can come out of that integration. And so now what we're saying is PA xp is equal to P integral of x dA. And so P's would cancel on both sides of the equation. We're setting those two equations equal to each other. And what you're left with is A xp is equal to the integral over the area of x dA. This is an old friend. So you may not believe this, but the professors talk to each other. And so I know in statics, you go over properties of areas and you actually develop these. If we just bring the area to the right-hand side of that equation and don't look at this side, this is known as the distance to the center of area, x bar. That is the definition. 1 over the area of the integral of x dA is the location of the center of area from some arbitrary y-axis. That's what it is. And again, you derive this in statics. So again, this is all review. So in this particular case, where we had a horizontal surface, uniform pressure distribution, as we said before, it should be intuitively obvious to you that the center of area and the center of pressure are the same point because you have a uniform load. And so here, the center of pressure is at the center of area. xp is equal to x bar. And again, xp is just where the force is acting. And we could do the same thing in the y direction, and you're basically going to find the same thing. Okay, so for a horizontal surface, the resultant force acts at the center of area. The center of pressure is at the center of area. And again, just to be completely redundant and boring, for a horizontal surface. Now, this is the review from statics. So we say that for any area and from any two axes, so for example, here is an x-axis and here's a y-axis, horizontal planes. These are horizontal, you're looking down on the surface. For any irregular surface, we have a center of area, let's call that G. And G has a coordinate x bar along the x-axis. That's the distance from G to the y-axis. And similarly, that's x bar, it's the distance from the y-axis. And then this distance here is y bar, and y bar is the distance from the center of area down to the x-axis. Nothing of revelation there. However, to complicate life, what we do is take the area, the total area itself, and multiply it by a moment arm to get its moment about either the x, that arbitrary X or Y axis. So we could take G and multiply it by its, the area A, and multiply it by Y bar, and that would give us the moment about the Y axis. And we could take A and multiply it by X bar, and that would be the moment of the area about the Y axis. That's known as the first area moment. So again, AX bar is the moment about the Y-axis. AY bar is the moment about the X-axis. It's the first area moment about the Y or the X-axis. If we take this nice rectangular area, again, this rectangular area has a measure Y bar to the center of area, and it has a measure X bar to the center of area. And so that's in the way, let me move it. So AY bar is M1. This is the first area moment about the X-axis. Same information from the last slide. But what we can do is take an area DA, any area, and in this case, it's parallel to the X-axis. And we can have then a moment arm Y. And what we would basically be doing is integrating YDA over the area, and that should give us AY bar, right? And that equation's on the next page. So again, the integral over the area of YDA is YA bar, and I bring A to the other side, and what do you get? Y bar is equal to 1 over A, integral over the area YDA. And that's just what we found when we were looking at the force on the horizontal surface. We were calculating for this location XP in the center of area, and XP turned out to be 1 over A integral over the area of XDA. And again, that's why I said this is an old friend. And in statics, you had these exact equations. So again, that's the first area moment about the X-axis, and about the Y-axis, you have that. So wait, there's more. That's the first moment, which from the name begs you to ask, well, what's the second moment? So for the second moment, what you would do is, again, take the total area, and in this case, take its moment arm. Let's say you're taking the moment of the total area about the X-axis. Its moment arm would be Y bar, the distance from the center of area to the X-axis. And now you would just square that moment arm. So before the first moment is AY bar, the second moment is AY bar squared. So similarly, what we would say is the second moment of an area, which is known as the moment of inertia, is equal to the integral over the area of Y bar squared. And again, if this is the axis that you're taking moments about, that distance to dA, if this is dA, is y, and the second moment, or the moment of inertia, of that area about the x-axis is y squared dA integrated over the area. And we typically call that IX, moment of inertia. I know you've heard of this before, because again, I talked to Dr. Bell.
Someone's asking what is the lower bound of the integral?
It's over the total area, so it would be 0. The lower bound would have to be 0 until we invent negative area.
Okay.
It's a chuckle, but you can have problems with fictitious mass or negative areas. So the other thing that you probably really hoping you would never see again is the parallel axis theorem. Not the parallel universe theorem, parallel axis theorem. So why do I say this? In that last slide, and I'm going to go back to it, we took moments about some location in space. And in this case, it happened to be the very bottom of the object. But that x-axis could be anywhere in space. A really convenient place for it is through the center of area. So what the parallel axis theorem allows you to do is move the moment of inertia from one place to another place. And if we have the moment of inertia about the centroid, that moment of inertia about the centroid is defined as the difference between the distance from some axis to the centroid, y bar, and again, that's subtracted from any distance along any dA to that same axis. So what you would do is take that y minus y bar term squared, you would expand that out, and then pass the integrand through each of those terms. And again, I'm not holding you to derivations, plus this is all review. So these two terms, if you look at this one, that's basically the definition. That's y bar a, that integrand. So you basically have minus 2 y bar a, which is minus 2 y bar squared a, and then you combine those two, and you get the parallel axis theorem. So what this says is the moment of inertia about the centroid is equal to the moment of inertia about some arbitrary x-axis minus y bar squared a. Y bar in this case is the distance between the center of area and that arbitrary x-axis. So if you look at this equation, if you use G for the center of area, IG, if you use C for the center of area, IC, the moment of inertia about the centroid is equal to the moment of inertia about any arbitrary axis minus y bar squared a. So that's the formula we just had. And what's convenient is to just move that term on the right over to the left. And what that says now is that the moment of inertia about any arbitrary axis x is equal to the moment of inertia about the centroid plus y bar squared a. Okay, so just switched one term around, and before we were focusing on the centroid, now we're focusing on some arbitrary axis. This is what will help when we're doing engineering analyses, this kind of equation. So again, the moment of inertia about any axis is equal to the moment of inertia about the centroid plus the product of the distance between the axes squared times the area. This number is always positive. Moment of inertia is always positive, or zero, could be zero. And y bar could be positive or negative, but you're squaring it. And then the area, again, we don't have any negative areas. So moment of inertia is always positive. And then similarly, we did this about the x-axis. You could do the same exercise for the y-axis. So in the back of your book, and I know this is really fine print, but again, this is in your book. It's in the first page of the appendix. They give you moments of inertia. And you have to pay attention about which axis they're talking about. So for example, for a triangle, for this rectangle, notice how they define the base, B, and the height, and the axis. So in this case, the moment of inertia, IXX, the moment of inertia about the centroid, that's IC, or IG, the moment of inertia about the centroid, is equal to 1/12 BH cubed. There may be a problem where you want the moment of inertia about the axis perpendicular to that, okay? So you need to be painfully aware of when you're using this, what it applies to in the variables. Likewise, if you're looking at the semicircle, it's the moment of inertia through the centroid. If you're looking at a triangle through the centroid, that is not the same if you're looking at it from a different side. So it's really focusing on the base that's parallel to that center of, area and the axis where the horizontal line is going through that center of area. So again, you have for a triangle 1/12 BH cubed, the base is on the bottom and the height is the vertical height. And you know from triangle that the center of area is h/3 from the base, 1/3 of the base height. All things you should remember. Maybe some of that gray matter has been killed, but let's just do a quick example. You have, from the back of your book, the moment of inertia is 136 BHQ. Here's a triangle. So we have the moment of inertia about the centroid, and we want to move it down to here. All right? And we know that the centroid, center of area, is 1/3 of the height away from the base. So the moment of inertia about the centroid, this is from the book. That's what was on the previous page. The moment of inertia of a triangle is 136 BHQ. I don't want the moment of inertia about this axis. I want the moment of inertia down here. And that's where we use the parallel axis theorem. So we have the moment of inertia about the centroid. That's the 136 BHQ. And what we need to do is add, that should be y bar squared a to that to get the moment of inertia about the bottom of the triangle. So again, this is IC, 136 BHQ, and this is y bar squared, and this is the area. And when you multiply those out, you get 136 BHQ plus 1/18 BHQ, which is 1/12 BHQ. Which is larger, the moment of inertia about the centroid or the moment of inertia about the base? Which is larger? I see BH cubed on both of them. So which is larger, 1/36 or 1/12? 1/12, right? So basically, the moment of inertia about the base is larger than the moment of inertia about the centroid. Haven't you ever seen in physics where you are spinning, say you're on skates, and you put your arms out and you go slower, and you put your arms in and you go faster, or you watch skaters doing that? It's the same principle. You're affecting the moment of inertia by doing that. So why are we doing this? Ultimately, we're going to have to do moment equilibriums. We need to know where forces act. And this may be of help to you. This was a review. And just something you probably never saw before, but I have to raise it to you. And that is the product of inertia. So before, what we were doing is taking the area and multiplying it by the distance to one axis, or we would multiply it by that distance squared to one axis. That gave us the first moment and the second moment. The product of inertia takes that area again and then multiplies it by the moment arm to one axis and the moment arm to the other axis. That's the x bar, y bar. And so there is a product of inertia about the centroid, just like before. This is parallel axis theorem. And there's the product of inertia about an arbitrary axis. That's the left-hand side, IXY. What is important for you to understand is the red text. If either one of the two axes that go through your location is an axis of symmetry, then the product of inertia is 0. Why? Because the moment arm, either x bar or y bar, is 0. Okay? That's something we're going to take to our advantage once we start doing some of these examples. So from slide 10 today, this is what we found. That the force on the surface is equal to the weight of the fluid above, and we can identify that that force is acting at the center of the area because we had a uniform load. That was the horizontal surface. So now what I want to do is just qualitatively talk about what's different if it's not a horizontal surface anymore. So let's just look at a vertical surface. On a vertical surface, what you see is, let me see if I did. What you see is at the top of this figure, we have a pressure here. So if this is HA, then the pressure here is gamma HA. And if this is HB, then the pressure down here is gamma HB. So you can see we have this now non-uniform pressure distribution. It's a trapezoidal pressure distribution. That's not a uniform pressure distribution. And so now you know that this resultant force is not going to act at the center of area. And if you look at the pressure distribution, if the center of area is here, just looking at the pressure distribution above versus below that center of area, what's below the pressure distribution that's below the center of area is larger than the pressure distribution above the center of area. And so typically what you're going to find is that the resultant force, which is acting at the center of pressure, is acting below the center of area. Now that's just qualitatively. That's what we should find. And it's because you now have a non-uniform pressure distribution. The horizontal surface had a nice uniform one. That's when life was easy. So we need to figure out the force, magnitude, and location. And we're going to go at it the same way. However, the first thing we're going to do is, instead of looking at just horizontal or vertical, let's say it's just inclined. This flat surface is inclined at some angle theta off of the horizontal. And what we're going to do is run the y-axis along the inclined surface. So the inclined surface is right here, and you're looking at the edge of it. So there's our surface. And again, if you look at the pressure distribution on that surface, it's not uniform because pressure increases as we go down in the fluid. And so we have a non-uniform pressure distribution. And again, pressure is a scalar, so I'm showing you it normal to the surface. And if we integrate that pressure distribution, we should get some resultant force F. And because we have a non-uniform pressure distribution, that force should be centrally located. It should not be acting at the center of area. Okay, so pressure distribution is everywhere normal to the surface, therefore F acts normal to the surface. The line of action of F is normal to the surface. Where does it act? It's going to act at what we call the center of pressure. For the horizontal surface, that was at the center of area. For a non-horizontal surface, it's going to be somewhere else. To find the magnitude of the force and where it acts, the center of pressure, we're going to use, again, the differential approach that we used before in the horizontal. We're going to slice this area up into differential strips, horizontal differential strips. Calculate the differential force on each one, dF, and then integrate over the area. So here is our definition sketch, and you can see that this thing is inclined theta to the surface again. And here is our surface again. It's highlighted in yellow. And if we look down on the surface, so our eyeball's here, eyeball is here looking down on the surface. This is the irregular surface you would say. Okay. So we're looking down on it, which means I think I put it up here. Okay, I'll get to it. We're going to slice this thing up into horizontal strips, dA. Why horizontal? Because the pressure on that horizontal dA is a constant. And for each dA, it's going to be submerged H. So again, when I look down on the object, what you're looking at is the x-axis, and this will be on the next slide. You're looking down on it now, and that's how you can see this thing. The x-axis actually runs along the fluid surface into and out of the page when you're looking at it from the edge. When you look down on it from this vantage point, you're then able to see that the x-axis is running along the surface. So, on each horizontal strip, we have a differential force dF. That force is equal to PdA the pressure on that strip times the area, differential area dA. And since it's a horizontal strip, that pressure is just the specific weight times the depth of submergence of dA. The surface, this plane surface is inclined theta off of the horizontal. So if we look at this surface being inclined at theta, so again, the surface is somewhere along here, or it could be that whole bottom piece. If this is the y-axis, then we're taking some measure, for example, y, and the x-axis, the origin is at the free surface. So y is measured from the free surface along the y-axis, the inclined axis, to a point of interest. In the vertical, from the geometry, we know that the vertical dimension, h, is equal to any y sine theta. So on the previous slide, we said we had each dA submerged h below the surface, or y along the inclined axis to that same location. So if this was the point of interest, we either can measure along the y-axis this way, or we can measure along the h-axis. Pressure is equal to gamma h, or gamma y sine theta at that point. And again, it's one of you who is the engineer who decided to put this gate inclined off of the horizontal, off of the vertical. Okay, so dF then would be equal to gamma y sine theta dA. So dF up here on the top is equal to PdA gamma HdA, which the equation that just came up below is gamma. Instead of h, we've got y sine theta times dA. Y sine theta replacing h. It's all coming together. So the pressure distribution acting over the surface area A has a resultant force F. F, the resultant force, is obtained by integrating all the little differential forces dF over all the little horizontal strips dA. So the resultant force F is equal to the integral over the area of all the little dFs. Remember, we took this irregular area and we divided it into horizontal differential strips of dA. And so again, from the last slide, dF is equal to gamma y sine theta dA. And the specific weight is constant and sine theta is constant. It's a plane surface. And so we pull gamma sine theta out of the integrand, and integral of y dA should start looking familiar to you now. So right now, we know y dA is, from what we just discussed, is y bar f. Any y dimension is measured along the y-axis that starts at the free surface. So y bar in this case is measured from the free surface down to the center of area of your submerged gate. Got it? So gamma h bar A, or gamma sine theta y bar A. Y bar we measure from the free surface along the y-axis. H bar we measure vertically from the free surface vertically down to the center of area, h bar. So again, y bar is the distance along the y-axis. H bar is being measured vertically. And we can get from one to the other from the sine of theta. Gamma sine theta y bar is equal to gamma h bar. Gamma h bar, or gamma y bar sine theta, is the pressure acting in a very specific location. It's the pressure acting at the center of area. Gamma h bar is H bar is the location of the center area. Gamma H bar is the pressure at the center of the area. Y bar is the location along the y-axis to the center of the area. Gamma Y bar sine theta is the pressure acting in the center of the area. So what you just discovered, if you're a golfer, F is equal to PGA. The resultant force, write this down, the resultant force of a fluid on one side of a plane submerged surface is equal to the pressure acting at the center of area times the area. I show you through the derivation irregular surfaces, surfaces that look like this. In engineering, we don't put in shapes like that. You could. They would probably cost an arm and a leg to build. What do we put in? We put in squares. We put in rectangles. We put in circles. So we typically have very simple geometric shapes. And for a square, you know exactly where the center of the area is, right? So for example, if I had an axis, here's the free surface. Here's my y-axis. And I'm not going to say what the angle is, but let's say at 5 feet, I'm going to have a gate that is 3 feet long by 10 feet into the board. So it's 3 feet along the y-axis and 10 feet into and out of the board. What's the distance along the y-axis to the center of area of that 3 foot by 10 foot gate? Well, you know that for a rectangle, that the center of area is half of that 3 foot distance from the top down to the center of area, right? So you would have the center of area, and it would be 1.5 feet plus the 5 foot of submergence to the top of the object. That's 6.5 feet. That's Y bar. That's not that difficult, is it? And now all you have to do is calculate the pressure there. That's where you would need the inclination. But again, because we always build nice symmetric objects, it's pretty easy to get these. So again, PGA. Now, I know I have half an hour left. I'm going to stop right there. Next time, we're going to start off, before I do an example, we're going to start off with figuring out where it acts, where the force acts. Right now, we just know the magnitude. Questions? Chat questions? Hopefully I was recording.